the recording. The center of mass has a special property is that when you trace the position of the center of mass in a trajectory, you will find that it just follows Newton's second law, just like a single particle. Okay, so if you have throw a hammer to the air, and although the hammer is rotating in air in a very complicated manner, if you trace the position of its center of mass, it will follow a simple projectile trajectory, just like a single particle in air. So you can describe the change in the position of the center of mass by using Newton's second law in the usual way. Okay, now we haven't discussed about rotation yet, so you don't know how to describe the rotation, right? That is a very complicated manner, which we are going to deal with it in the next chapter. But even in this chapter, we know about the center of mass equation. The center of mass equation is just like the same, you just take the same form as the Newton's second law for a single particle. So it follows a simple projectile motion in air. So that's a nice thing. In this lecture, we're going to calculate the center of mass position. Now we have this formula. We introduced this formula as a position of the center of mass. And here, let me see. Now, this you should notice that this formula is a vector equation, and the vector equation involves the Ri. Okay, Ri is the position vector of the I particle. So that means I can decompose this formula into three scalar formula. Okay, because each vector Ri has the x component xi, y component yi, and z component zi. Therefore, if I take the x component, y component, and the z component of the equation, I will end up be able to locate the x coordinate, the y coordinate, and the z coordinate of the center of mass. So this is the idea. Okay, so if you have a system of particle like this, I can divide the system into many particles, and for each of the particle, I have a position given by the I particle have a position given by Ri. If I form a sum of the product of the mass and the position vector and divided by the total mass of the system, I will be able to get the position of the center of mass. And so the motion, the complicated motion of all this particle can be described by the position of the center of mass, which I call the big capital R. Okay, so that simplifies the problem a lot. Although we don't know how to describe the rotation yet, we still be able to describe the position of the center of mass. And there are pretty much example in using the center of mass that you can see in daily life. For example, I don't know whether you have played with this game, the Angry Birds. I think about a few years ago, I don't know, are you too small at that time? Was you too small at that time to play with the Angry Bird? Now, that video game, that game is interesting because they use the Angry Bird to bomb the pig. Okay, and in some of the scenario, you see the Angry Bird, it decomposes into several parts. Okay, when it decomposes in, for example, Angry Bird decomposes into 3 Angry Birds, small Angry Birds. You can see the center of mass is in the middle Angry Bird. So if you trace the trajectory of the middle Angry Bird, then it also follows the simple projectile motion, just like as if the birds had not decomposed. So this is an example of a video game using the center of mass concept. If you look at the firework, after exposed in air, the pieces will fall down under gravity. But if you look at the position of the center of mass, is roughly follow the trajectory of a single particle falling down. Okay, so that is again another example of the center of mass. You know the star Sirius. Sirius is the brightest star in the sky, apart from the sun. Okay, and astronomers found that Sirius is not a single star. It is a binary system. You have two stars. Sirius A is a bright one, and Sirius B is a dimmer one. The dimmer one is a white dwarf. Okay, it's a small star, but with a high density. That is a white dwarf. Now, Sirius A and Sirius B, they are revolving around each other. Okay, so there is a center of mass that governs the rotation of the system. And the center of mass position actually is moving in space. So as seen from the Earth, we will see that the center of mass is moving through space, and the Sirius A and Sirius B are revolving about that common center. Okay, so you imagine the center of mass to be in visible position here, and Sirius A and Sirius B, they are both revolving about that invisible center of mass position. And the center of mass position is moving relative to the Earth. So you will see the Sirius and Sirius B, they are revolving about a invisible spot, which is moving along in a straight line, as seen from the Earth. Okay, so you see the change in the position of the two stars with time. This is a span about a century. You can see the period of the two stars has a very long period. Okay. Now, so the center of mass concept holds even for a system that is not a rigid body. A rigid body means a body that cannot be deformed. Okay. For example, this cup is a rigid body because it cannot be deformed. But if you say this book is not a rigid body because it can be bended, it can be deformed, or in some situation, the system can be decomposed into several particles moving independently. But even if the system consists of particle rectangle moving arbitrarily, even if they are not bounded together, the center of mass concept still holds. If you trace the position of the center of mass, they still follow a Newton's law of motion, Newton's second law of motion. Okay, so that is an amazing thing. Okay, I would like to share with you some simple concept in order to make you understand more about the concept of center of mass, and that is the concept of weight mean. Okay, now suppose we have a 3 kilogram and 5 kilogram mass. They are located at the x position of 2 and 6 respectively. Okay, so we consider only the one-dimensional system. Okay, the center of mass position is obviously located at along this line. But how to find x? Well, it's simple because we know the formula. It's what? We form a sum of the mass times the x coordinate, and we divide it by the total mass. That is a formula. Okay, so how do we find it? We first take the 3 kilogram mass, and then we multiply by 2. 2 is the x coordinate of the first mass. So we have 3 times 2, and then plus, because it's a summation, so you have considered the other mass also, and 5 kilogram times 6. Okay, the mass times the position. So you sum them up, and you divide by the total mass. The total mass of the system is a sum of the individual mass, so it's 3 plus 5. Okay, so when you put in all this number, you find that the position x of the center of mass is as 4.5. Okay, now you obviously you will find the position of the center of mass closer to the heavier mass. It is closer to the 5 kilogram mass than the 3 kilogram mass. Now, because the center of mass is a weight mean, if you have a larger weight, if you have a higher mass, then you carry more weights. Okay, and so the center of mass will be closer, will be getting closer to the mass with the heavier weights. Okay. Now let's recall you with a simple example that you might learn in high school statistics. Okay, now suppose we have 30 students We have 30 students, and they have different heights. And suppose we measure the range, we categorize the height of the student in terms of social range. And on the average, we find that there are 10 students with heights in the range of about 160 cm, and 2 students with the height in the range of 165, and 80 students having the height in the range of 170 cm. Okay, so these are the frequency, right? 10, 2, and 18, they are the frequency of appearance of these quantities, of this height. Okay, so when you want to calculate the average height, you may simply add up all the heights, which consists of 10 of 160, 2 of 165, and 18 of 170, and you divide by the total number of students, right? Now, we can also do it in another way. Instead of adding 10 of 160, we just multiply 160 by 10, and we multiply 165 by 2, and then we multiply 170 by 18. That is, you multiply the heights by the frequency of appearance, and you add them up together, and you divide by the sum of the frequency. The sum of the frequency, of course, gives you the total number of students in this situation. Now, so if you take the blue numbers as M, this is M1, this is M2, this is M3, and in the denominator you have M1 plus M2 plus M3, right? And you take the heights of the student, the red numbers, at X, X1, X2, and X3. Then the formula for finding the average height will be exactly identical to the formula for finding the center of mass. Okay, so you see what the center of mass means. It is a kind of weight mean. If the frequency, in this situation, if the frequency is large, you have a high weight. Okay, and in the case of the center of mass, if a mass has a higher mass, which is more heavy, then it has a higher weight in this in the position. So it carries more weights, and the position of the center of mass will be closer to it. Okay, so these two situations is completely analogous to each other. So you may think of the mass as a weight. So you find that the weight means of the position of an object. Okay. Now let's look at this example, the two-dimensional example. You have 3 kg, 4 kg along the x-axis, placed along the x-axis, and a 5 kg mass placed on the y-axis. And the coordinates are given in the red numbers. Now we find the in this situation, the y component of the center of mass is not obvious, and also because of the 3 kg and the 4 kg, they are not symmetrical. So the distribution is not symmetrical. So the x-po coordinate are also not obvious. So you have to go back to the formula to find the x and the y component of the center of mass position respectively. Okay. For the x position, you have summation mixi divided by the total mass. Now, so we look at the individual mass. For the 5 kilogram, the x coordinate is 0. So we have 5 times 0. And then for the 4 kilogram, the x coordinate is 1. So you have 4 times 1. And for the 3 kilogram, you have x coordinate equal to -1. So you have 3 times -1. And you add them up together, divided by the total mass, which is 5 plus 3 plus 4, and that is 12. Okay, so eventually after doing the calculation, you find the x coordinate to be 1/12. For the type 5 coordinate, you do the similar thing. You take the mass first, 5 kilogram, multiply by its y coordinates, which is square root 3, and then 4 kilogram multiplied by its y component, which is 0, 4 times 0. And you have the 3 kilogram again multiplied by its y coordinates, which is again 0. So the last two terms does not contribute. And you find that the y component when you divide it by total mass, you find the y component of the CM position to be 5 square root of 3 over 12. So it's somewhere here, okay? You see that it is closer to the 4 kilogram mass than the 3 kilogram mass. So it is on the positive X side, okay? And because there are more masses at the base than at the top of this triangle, so you can see this center mass position is closer to the x-axis than to the 5 kilogram mass. Because the 4 kilogram and the 3 kilogram, they add up to 7, which is larger than the 5 kilogram on the top. Now here we come to the difficult part. Now we start with the calculation of the center mass. We start with this definition for a system of discrete point mass. So the system, we imagine the system can be divided into many small pieces, right? But that is not quite convenient for calculation. In the real world, the mass distribution almost always come in a continuous manner. We cannot simply divide it into a lot of small pieces, but they come in a continuous object, a continuous distribution. So in order to transform the calculation of center of mass from a discrete distribution to a continuous distribution, we have to make use of integration. Okay, integration is simply a continuous version of the summation. Okay, so when you divide a continuous system into infinitely many small pieces, you sum them up all together, and that forms an integration. Now let's see how we do it. Okay, suppose we have a continuous mass distribution. For simplicity, in my diagram, I only draw a lamina, a thin lamina on the XY plane, but you can always extend it to 3 dimension. It doesn't matter. It's only for the ease of drawing that I draw it as a 2-dimensional object. Okay. Now, so we chop the lamina into a lot of small pieces. Theoretically, we do it infinite, many times. So each of the pieces become infinitesimal. Okay, and for the eyepiece, I call the mass on the eyepiece delta mi. This is the mass in the small area, in the eye small area. Okay, and the position vector, the position of the eyepieces relative to origin, it is described by the position vector Ri. Okay, and of course Ri has 2 components in the Cartesian coordinate in 2 dimensions. The x component is xi, the y component is yi. Okay, so the Ri defines the position of the eye mass of the eyepieces. Okay, now let's see what the formula tell us. It tells us to form a summation of the mass times its position vector. That is what the center of mass formula tells us. And then after doing the summation, you divide by the total mass of the system. Okay. Now, but here we don't have a discrete point mass, but we have small pieces. The small pieces is called, the mass of a piece is called delta mi. So we have delta mi here instead of mi. The delta here means the mass in these very small pieces. Okay, so we have delta mi multiplied by Ri, which is its position vector, and we form a summation over all these pieces. Okay, and we divide by the total mass m. In the limit where delta m is getting very small, we imagine we divide it into smaller and smaller pieces. Okay, the d delta m would become very small. And when delta m is becoming very small, it becomes dm. In integration, dm means a very small pieces of m, of the mass m. So the summation in this limit will become the integral of the position vector of this mass over dm. So the summation delta MIR now becomes the integral of R over dm. Now we should notice that it is R dm, but not MdR. Because dm refers to the small pieces of mass in the summation. And that is the integral variable to be integrated over. So we integrate the R over the dm, where R is the position vector. This is not the small pieces. This is not the the position of the ith mass, right? The delta goes with the dm, goes with the mass itself. So delta mi become dm, but R still remains to be R. Okay, so please notice that it is R dm, but not MdR. Okay. If you like, you can decompose because of the ease of calculation. You can decompose this formula into two components. For the x component, you have integrate x dm over the total mass, while for the y component, you have integrate y dm over the total mass. Okay. Now, but the problem is how should we do this integral? How should we do this integral? We don't know how to handle this dm. This dm is rather abstract, right? Now, in the next slide, we will illustrate to you how to find this dm with an example. We will be able to express the small pieces of mass in terms of the coordinates, in terms of the x and the y coordinates. And by doing so, you can evaluate this integral rather easily. Okay. Now let's deal with this example. We have a semicircular lamina, a uniform semicircular lamina. It means a thin sheet of material with negligible thickness, and that material takes a shape of a semicircular object. So you imagine now you have a semicircular lamina like this. And of course, if I place the semicircular lamina about the symmetric axis, which is the y-axis, the center of mass position must be along the y-axis because it's symmetrical on both sides, right? But I don't know the heights of the center of mass position above the x-axis. Okay, the x-axis is the axis where I place the base of the semicircular lamina. Okay, so how are we going to find it? How are we going to find the dm and integrate with the y divided by the total mass to get the y position of the center of mass? How we are going to do that? Now the trick is we now divide the semicircular object into a lot of horizontal strips. By horizontal, I mean the strips that are parallel to the x-axis. Okay, so you now chop the lamina into a lot of small strips, and the thickness of each strip I call dy, because the y changes very small by a very small amount along the width of the strip. So I call the width dy. Okay, and the heights of this strip above the x-axis is called y. Okay, now you see at every point on the strip, they are at equal heights with the x-axis. And that's why I chop it this way. Okay, because we have a well-defined y for each strip. Okay, if you choose to chop the lamina in vertically, then I don't know what is y, because different points will have different heights above the x-axis. So the y is not well defined. But if I chop it horizontally parallel to the x-axis, each of the point here, because the strip is so narrow, so each of the point on the strip has an equal distance y from the x-axis. So the y is now well defined. Okay. Now let's calculate how much mass are there. What is the mass of the strip? And we do it by using the density, the concept of density, because the lamina is uniform. So we can use the concept of density to find the mass on this yellow strip, on this orange strip. Now the total mass of the semicircular lamina is m. So if I divide the total mass by the area, I got the mass per unit area, which is the density, right? The total mass is of course m. And for a semicircle, the area is pi r squared divided by 2. Pi r squared is the area for a full circle. Now it's only a half of the circle. So I get the density as 2m over pi r squared. Okay. Now in order to find the mass in this strip, I first have to calculate its area, right? Because I know that the area multiplied by the density will give me the mass. Because the density now is the mass per unit area. So if I got the area of the strip and I multiply with the density, I will be able to get the dm, which is the mass of this narrow strip. Okay. Now the difficult part is here. How do we find the area of the strip? Now it's not that difficult. Let's look at the geometry. Now we look at this length. Now because the radius of the circle is r, and the height of the strip above the x-axis is y. So this is as long as this is a right angle triangle, we can use the Pythagoras theorem. The Pythagoras theorem says this length, the opposite side of the triangle, is equal to the square of the hypotenuse, r squared, minus y squared, square root. Okay, y is the length of the adjacent side. So this length is big R squared minus y squared square root. Okay, and of course we have two sides, right? This is only one side, and we also have the other side. So we multiply the result by 2. So we have 2 square root R squared minus y squared. But this is only the length of the strip. We still have to multiply by its thickness. The thickness is dy. When we multiply the length of a strip by the thickness, we got the area. And when we multiply the area by the density, we got the mass. Okay, so you see when I do this, I have successfully converted the dm into dy. The dy is the y is the coordinate. So if I convert the dm into dy, that means the integration can be done over the y coordinates. And that is a trick. That's the important trick. If I'm not able to do this, I cannot integrate over. Now everything is expressed in terms of y, so I can integrate over y. Okay. Now I put it back. I know the density is given by this, so I put this constant back. And after tidy up the constant, I get this expression. But still, I have to put this bunch of thing back to the formula. I still have another y here, right? That's y is to be integrated. This branch of things is only dm. Okay, so I put dm back to this formula, and I end up with what? This is the dm. The red thing is the dm. I still have another y to be integrated over. So the 4m over pi r squared is a constant, so I move it out, and m get cancelled. And inside the integrand, I now have a y multiplied by the square root of r squared minus y squared. And I have to integrate over y. Now, what are the limits of the integration? We take a look at this diagram again. The minimum y is, of course, the x-axis, right? We consider a lot of horizontal strip. They are parting up. The lower strip is at the x-axis, which is y equal to 0. So what is the highest strip? Where is the highest strip? The highest strip is here, right? At the top of the semicircle. At the top of the semicircle, the y coordinate is r, capital R, which is the radius of the circle, right? So that means I integrate from 0 to capital R. Okay, I integrate from the x-axis up to the top of the semicircle, which is R. Okay, so I'm involved in doing this integration. How do we do it? Well, I find that it can be done by change of variable. Okay. Now you can easily see that if I put the y and dy together, y dy become dy squared over 2. So the dy squared, the y squared inside the d actually match with this y squared inside the square root sign. And so I can do the integration. So it's natural to make a change of variable to u, which is r squared minus y squared. Okay. So I define u by r squared minus y squared. And if I differentiate both sides, I find that du is equal to minus 2y dy. The r is a constant. I differentiate y squared, I get 2y dy, and with a minus sign. Now, how about the limits? With y is 0, I get u equal to r squared. So the lower limit now become r squared. And when y is equal to r squared minus r squared is 0. So u is 0. And the upper limit will now become 0. Okay. So the square root here will become square root u. And from this formula, I can see that the y dy now become 1 minus 1/2 of du. The y dy now become minus 1/2 multiplied by du. So I put it back to this integral. Now this integral is easily can be easily integrated. Okay, it is just u to the power 1/2. So by doing integration, I find that the result will be u raised to the power of 2/3. Okay, divided by 3/2. And I evaluate the upper and the lower limit as the upper limit being 0, the lower limit being r squared. Okay. And after some manipulation, I eventually find that the center of mass position is 4r over 3 pi. Now you can, if you use your calculator to calculate the value of 4 over 3 pi, you will find that its position, the position of the center of mass, is smaller than alpha 2. Okay, it's smaller than alpha 2, meaning that the position of center of mass is closer to the base, is closer to the y-axis than at the top. Now, why is it so? You look at the diagram and you understand why. Because the semicircle is wider at the base than at the top, right? At the top, there are less mass, but at the base is wide, so it has a larger amount of mass there. So the position of the center of mass will be closer to the base than at the top. So it means that the center of mass position must be smaller than half of r. Okay, and that's why we got this number. Okay, but in order to get this number, you have to do integration. Okay, there's no excuse. You have to do integration to find it. Now you may want to know how would be the case of a triangle. For a uniform triangle, where will be the center of mass? Now I told you the answer. The center of mass of a uniform triangle is at the centroid of the triangle. Okay. Now what is a centroid? I first introduced to you this concept in case you haven't heard about it. Now this is a triangle. We divide the side into 2 equal parts. So there's a point here, there's a point here, and there's a point here. Okay, these two halves has the same length. This 2 half again has the same length. This 2 half again has the same length. Okay, so I join the vertex to the opposite middle point. Okay, and that defines the centroid. And 3 lines will cross at the centroid of this triangle. Okay, so the centroid is where the perpendicular bisector of the opposite side meets. Okay, there are 3 bisector of the opposite side. When they meet at one point, that point is the centroid of the triangle. Okay. Now it can be found by using geometry. I will not go into details here. It can be found by using geometry, simple geometry, that the position of the centroid above one of the side of the triangle is equal to 1/3 of the height of the triangle. So if the vertex is h as a height h above the base, the height of the centroid above the base is h/3. Okay, you can prove it with simple geometry. I will not teach you how to do it now. You go back to your high school textbook. Okay. But by using integration, I will be able to show that the center of mass of a triangular lamina is exactly at the centroid of the triangle. Okay, so if I do an integration to find the height of the center of mass, the y coordinate of center of mass in for this situation, I will find that the y coordinate of the center of mass is exactly h/3, where h is the height of the triangle. Okay. Now, how do we do that? We go back to the formula, integrate y dm over capital M. As we know, the density of the triangle will be the total mass of the triangle divided by the area of the triangle. And for this triangle, we have h as a height and b as the base. So the area of the triangle is half h multiplied by b. Okay, half the height multiplied by the base is the area of the triangle, right? Now again, we divide the triangle into a lot of strips, which are parallel to the x-axis. So again, the height is dy, but how do you find the width? Well, we find the width by similar triangle. Okay. What is the similar triangle that is involved in this situation? Now you see this triangle and this triangle, the large triangle and the small triangle here, they are the similar triangle, right? And then you have this height, the height of the small triangle. The total height of the big triangle is h. This height is y. So this height is h minus y. So by similar triangle, you have what? You have h minus y. This is a small height, the height of the small triangle, divided by the height of the big triangle, which is h, equal to the length you want to find. This is the length you want to find, divided by the length, the base of the large triangle, which is b. Okay, the length you want to find is actually the base of the small triangle. Okay, so this is just a similar triangle you learn in high school, right? So I got the length L of this strip as what? As 1 minus y over h multiplied by b. Okay, so you have the length of the strip multiplied by as 1 minus y over h multiplied by b, multiplied by the thickness of the strip, dy, will give you the area. So this is the area of the strip. And if you multiply the area by the density, you got the dm, right? And you put all the things back to this formula, you can integrate over to get the center of mass position, the y coordinate of the center of mass position. And eventually, after doing all this integration, you should be able to find that the y coordinates is equal to h/3. Okay, now I leave it to you as an exercise. Okay, you try to complete it in your homework. I outline all the methods for you so that you will not be you will not find it too difficult for to do the calculation. Okay, but it is important for you to understand the concept. Okay, so if you don't understand it, you just review this part of my teaching, and until you understand it, you go to do the homework. Okay. Now I better stop, have a break here, because the calculation that we have just introduced is rather complicated. So let's have a break for 10 minutes. And after that, let's come back to this more complicated problem of the composite center of mass of two bodies. And then we have an extension on the variable mass system, on a system that involves a changing mass. and we will see how we use the concept of momentum to solve that problem. Okay, we will be relying on the concept of conservation of momentum to solve a variable mass system. Okay, so let's take a break here. Let's continue with our discussion of the center of mass. We were somewhere here, right? Now, in this example, we will try to find the center of mass position of two composite of a composite body. This body is composed of two or more objects. Okay, and for simplicity, we make it two, and the argument can be easily generalized to n object. Okay, we suppose the center of mass of the first object we call A, is at RA, while the center of mass position of the second object, which we call B, is RB. Okay, so RA and RB are the center of mass position of the first and the second object, and we want to find the composite, the center of mass position R of the composite object. So the formula tells me that we have to form a sum of all the sum of all mi multiplied by the position vector of Ri divided by the total mass of the system. Now the I here denote the position of the individual small masses in this two area, right? Now, so the sum here will include both area A and area B. It includes both objects. Okay, but since it's a summation, I can always decompose the summation into the summation over A and the summation over B, because they are just added together, right? So we can decompose this total sum into a summation over object A and a summation over object B. Okay, and then add them up together. Okay, but here comes the trick. Now I divide the summation over the object A by the mass of the object A. And then I multiply MA, the mass of object A again. So the MA will cancel, meaning that I've done nothing. And similarly, for the sum over object B, I divide and multiply by MB, the mass of object B. And for the total mass of the system, I now write it in terms of the mass of object A plus the mass of object B. Okay. Now, how do I do this? When I do this, I realized that the summation of MRI divided by MA over object A is just the position, by definition, the position of the center of mass of object A. While the summation MRI over object B divided by the mass of the object B is just the position of the center of mass of object B. So I now arrive at the formula. The formula is the center of mass position of the composite object being equal to MARA plus MBRB divided by MA plus MB. Now you can see this combination is the same as treating MA and MB as a point mass. We can imagine MA and MB are 2 point mass, which are located at the center of mass position, R and RB. And so this will now be the center of mass position of the object combined. Okay. Okay, so you can imagine the center of mass is a position where all the mass of the object seems to be concentrated at. And even if you have two extended bodies, you may now consider them as point mass located at the center of mass position and use the formula we learned before to find the position of the composite center of mass. Okay. Now let's have this example. Suppose we have a lamina that takes the shape of a house. Okay, you have a equilateral triangle as a top, as a roof of the house, and you have a rectangle, a square, as a main body of the house. Okay, so the two parts combined together, and we are now required to find, and of course they are of the same density. And you are now required to find the center of mass of the composite body. Okay. Now, first find the mass of the triangle. the length of the side of the triangle is A. And since this is an equilateral triangle has angle equal to 60 degrees, right? So the height of the triangle is A sine 60 degrees. Sine 60 degrees is square root 3 over 2. So the height is square root 3 over 2A. For the area of the triangle, I have 1/2 multiplied by the base, which is A, multiplied by height of the triangle. So we put back H equal to square root 3A over 2, right? And we got this area, square root 3 over 4A squared. And the centroid of a triangle, and the center of mass of the triangle is at the centroid. The centroid is at the position as a height of H over 3 above the base. And so that means if I measure everything above from the x-axis, the center of mass of the triangle is now A, the height of the square, plus H over 3, the height of the center above the base of the triangle. So it's A plus H over 3, but H is square root 3A over 2. So I got 1 plus square root 3 over 6A, okay? And for the composite object, I have MAYA plus MBYB divided by MA plus MB. MA is proportional to the area of the triangle. By A, I mean the triangle. So MA is proportional to the area of the triangle, which is square root 3A squared over 4. And the position of the center of mass of the triangle is now given by this. So I put it back here, okay? Plus the area of object B. Object B is a square. So the mass is of course proportional to the area of the square. So it's given by A squared, okay? And the position of center mass above the base is of course half of the side, which is A over 2. And the sum of the mass of MA, sum of the mass of A and B is of course the sum of the area. Now notice that there's a density here, but the density doesn't matter. Eventually, if I put the density sigma here, the density in the numerator will be canceling with the density in the numerator. Okay, so the actual density doesn't matter. Okay, and after doing some calculation, I find that the y is given by this. This is my answer. I think you can do it. Try to do it at home. Okay. Now, an important property about the center of mass is like this. The center of mass position is actually independent on the coordinate you choose. Now, when we talk about vectors, we continuously emphasize this property of vectors. Why physical laws are written in terms of vectors is because vector can express the position of a physical quantity that is independent of coordinates. Okay, the vector has a property that is independent of coordinate. No matter how you choose the coordinate, you might choose a coordinate to be in a horizontal or vertical position, or you might tilt the coordinates, or you may rotate it in an arbitrary manner. Although the components of the vector will change, but the position that the vector specifies will not change. Okay, so that is an important property of the vectors. And also, the dot product and the cross product, the result of the dot product and the cross product will not be changed by a rotation of coordinates. Okay, now we are going to show to you that the position of the center of mass defined by this formula does not depend on coordinates. Okay, so if you use another coordinate to calculate the center of mass, you will find that it still refers to the same position of the object. So that means using whatever kind of coordinate you to calculate the center of mass is not important. It always will give you the same position. Okay. Now suppose we have two different coordinates. One coordinate is centered as position O. The other coordinate is centered as position O prime. Okay. So the center of mass position is here. This is an extended object with a center of mass position here. So I can see the center of mass position with respect to the coordinate O with center O is R, while the center of mass position relative to the coordinate O prime is R prime. So I denote everything relative to the new coordinate by a prime. Okay. Now, how about a mass in general? Suppose I divide a large object into many small pieces, and for the piece Mi, its position relative to the unprimed coordinate is Ri, and its position relative to the prime coordinate is Ri prime. Again, I'm using a prime to denote the position relative to the prime coordinate. Okay. So according to our formula, we have the position of the center of mass given by summation MI/RI vector divided by the total mass. Now, but you can see the position of O and O prime, they are just different by a constant vector. And I call this constant vector the D. The D translate my O coordinate to the new coordinate center. Okay. And when I look at the point mass, the small mass here, the Mi here, its position are specified by Ri and Ri prime respectively relative to the O and the new coordinates. And you can see Ri prime, and D, the three vectors now form a triangle. Now this is a very obvious triangle here. Okay. And by the addition of vector, I can see that Ri prime is equal to Ri is equal to Ri prime plus D. Okay. The vector sum of D and Ri prime would be Ri. Okay. So in the summation, I can now replace my Ri with Ri prime plus D. Okay. Just by this triangle. Okay. A simple vector addition. Now, because this is a summation, so the summation can be distributed to each of the term, right? So I can separate these two, okay, in the summation. So for the first term, I got summation Mi/Ri prime, while for the second term, I have summation Mi here, and the D, because it is a constant, right? It's just a constant, so it can be taken out of the integral. It can be taken out of the summation. So I sum all the M first and then multiply by D. Okay. Now you can easily see that the first summation after dividing by the total mass is just a new position of the center of mass. The position of the center of mass relative to the prime coordinate, relative to O prime, right? Because the summation now involves the Ri prime. So summation Mi/Ri prime divided by M will be the center of mass position relative to the prime to the prime coordinates. Okay. And how about the second term? The second term consists of summation Mi, which is the total mass M. When the total mass divided by M is of course 1, and we are left with the D. Okay. So the equation is very simple. The R vector is equal to the R prime vector plus D. But what does it mean? Well, we find that it just means this triangle, the large triangle. When I look at this vector R, the big R is equal to what? R prime plus D. Okay, this is again a simple vector addition. When I add R prime to D, I get R. So what does this equation means? It means that the vector R and R prime, although they come from different coordinate origin, they are referring to the same position in the object. Okay, so no matter you use the coordinate R prime and R to do the calculation, you still end up with the same position of the center of mass. And that means the center of mass is independent of coordinates. Okay, so that's an important property. If you find that the center of mass is different, it goes to a different position when you use different coordinate, then it is not intrinsic property of the material. It's not intrinsic property of the object. And the center of mass concept will not be useful. Okay, the center of mass concept is useful because it is a position where all the mass of the object seems to be concentrated at. And that should be independent on whatever coordinate you choose to do the calculation, okay? Now let's take a particular case. In particular, if we put the coordinate origin O prime to be exactly at the position of the center of mass, then all the Ri if I put the new coordinate origin to be exactly at the position of the center of mass, then the vector R prime will be 0, right? Now, R prime is the position of the center of mass relative to the origin O prime. If I now choose my O prime such that it coincides with the CM, R prime will be 0. Do you see that? And when my R prime is 0, it means that because R prime is R minus D, it means that R is equal to D. So you can see ECC's diagram that my D is actually the R. R and D are the same vector. Okay. So you can see the R prime, which is summation MI prime divided by capital M, is now 0, meaning that the summation is 0. Now, because we choose this position to be so special, we choose the prime coordinate to be now exactly as a position of center of mass. So it may be more convenient or more explicit to call this R prime RCM, where the superscript CM now denote the position vector relative to the center of mass. So what I mean, RICM is the position of the I mass relative to a position vector, which is directly point out from the position of center of mass. So this Ri prime, actually now I refer to RICM. So I now have this formula, summation MIRICM to be equal to 0. So that means the first moment, if I take a summation of all MIRI prime about the center of mass, I will find that it sum up to 0. Okay. Now this is very apparent. Actually, this formula looks a little bit abstract, but I can let you see the meaning of this formula with a simple example. Okay. Now let's look at two boys balanced on a seesaw. The two boys may have different weights. Okay. Suppose the mass of the first boy is M1, the mass of the second boy is M2. If they are able to balance at the pivot of the seesaw, then the center of mass must be at the pivot point, right? So this is a center of mass position. And the coordinates of the two boys relative to the center of mass position, I denoted by R1CM and R2CM. Now the position vector, now I have a superscript CM. That means now I measure the position of the boy relative to the center of mass position. I use the center of mass position as my origin. Okay. And by a simple balancing of moment you learn in high school, you can see that M1R1 CM is equal in magnitude to M2R2 CM. And if the two vectors are in opposite direction, the sum of these two terms will become 0. And that simply means the two boys now balance at the center of mass position, right? That is a simple moment equation you learn in high school, right? If you multiply the equation with a G, that means the balancing of moment on both sides of the seesaw. Okay. Now this is a simple example of this summation, and in fact you can generalize it to arbitrary distribution of mass. If I chop a body into many small pieces, and I form a sum of the mass of each pieces with its position vector directly direct outward from the center of mass, I form a sum, I will find that it is 0. So the moment, the total moment of each pieces of all the pieces of the body above the center of mass, they sum up to 0. Okay. Now, before going further, I would like to give you this interesting example of that concept of center of mass. Now, this is just a extension. I will not test you in the final exam, but I find it this example very interesting, and so I introduce it to you. Now, Forsberg is a USA high jumper. He break the world record of in the Olympic Games in 1968. He invented the so-called force-free in back jump. By back jump, what we mean is that when you do a high jump, you actually hop over your body over the pole, right? Before Forsberg, people do it with the face facing ground. So he just lop over the pole with the whole body facing the ground. But Forsberg do it in the opposite. He did it with the back facing the ground. But when he did it like this, he found that it would be much easier for him to jump to a great height. And so he broke the world record several times. And after Forsberg, not almost every athlete after 1988, they jump with the back passing through the rope. Okay, so that is invented by Forsberg in 1968. Now we will be able to see why passing the pole with the body with the back hovering over the pole is an advantage by considering the center of mass. Now, let's see this video. I share with it now, but with the optimization for the video. Now, the center of mass of a normal person is somewhere in the abdomen. Okay, somewhere here. So let's see how would the center of mass position change when the Atlantic hover over the pole. We jump over the pole. Now, this is a jump before Forsberg. When he jumped, now this is a back jump, okay? When they do the back jump, Forsberg bent his body. He bent his body such that when he passes the pole, the position of the center of mass is below the pole. Okay, he bent it so large into a large extent such that the center of mass of his body just passes the pole below it, okay, instead of over it. So that will be pose an advantage because he requires less energy to raise his body. Okay. Now this is the type of jump that people did before Forsberg. You see that the center of mass position is above the pole. So which kind of jump will save more energy? Of course, Forsberg's jump will save more energy. Okay, because it only requires a lower position of the center of mass. If you do it like this, you need to raise your body above the pole, right? The center of mass above the pole. While if you do the Forsberg jump, if you bend your body sufficiently by a sufficiently large amount, you actually will lower the center of mass position below the top of the pole. And that, of course, poses an advantage because it requires less energy for you to do this. Okay. So Forsberg's contribution to high jump is revolutionary. Before him, nobody had thought about that. But after him, almost all the high jumpers, they do it with the back, okay, instead of just hovering over with the front body. Okay. Now let's go to the last part of this chapter, which is the variable mass system. Now this part will not be examined. Now in some system, Newton's second law for mass m reach like F equal to ma, right? But in some system, it is difficult to apply Newton's second law in this form. The reason is for some system, the mass is not constant, but is a variable. And that happens in continuous system where you have continuous mass transfer. For example, a rocket ejecting field. When the rocket proposes itself in the sky, fields are continuously being ejected, right? So the mass of the rocket is not a constant. It will decrease with time. When the fields are ejected and continuously being ejected, the mass of the rocket will be decreasing. So you don't know what the mass m means in the equation F equal to ma. So you cannot apply Newton's second law in the usual form. Okay. And another example is what you find in a moving cart, for example, in a supermarket. When you place object into the cart, its mass will increase, right? So again, you cannot apply Newton's second law in the usual form. And for this kind of problem, we should go back to momentum consideration. I'm not going to teach you the general method, but I only want to illustrate to you how to do it with an example. And that example is a rocket ejecting field. Now, suppose I have a rocket, that's a schematic rocket. A rocket ejects field at a constant rate of kilogram per second. And that means the rocket ejects kilogram of gas per second, okay? And it does so with at a constant velocity. The velocity is relative to the rocket, okay? And that velocity is u. So as seen by an observer inside the rocket, he will see the field being ejected out at a speed of u meter per second. That is the velocity relative to an observer inside the rocket. Okay. But relative to an observer on the ground, the rocket itself is moving. So the field velocity is not just u relative to an observer on the ground. Okay, because the rocket itself is moving forward as a velocity v, right? So the velocity of the field relative to the ground, it is not equal to u, but is equal to v minus u, where v is the velocity of the rocket. Now we define the positive direction to be the right, which is the direction of the motion of the rocket. So v take on a positive sign and the u take on a negative sign for the field. Okay, so v minus u is becoming the velocity of the field relative to an observer on the ground. Okay, now here we apply the idea of relative velocity, because when we describe the motion, we always refer to a stationary observer. We always refer to an inertial observer, right? Inertial observers are legitimate to describe the motion using Newton's law. So in this situation, the rocket itself is accelerating. The v is changing with time. So the rocket is not an inertial observer. But we have to go back to inertial observer. So we rely on observer on the ground. And we should measure every physical quantity relative to the observer at rest, relative to the observer on the ground. Okay, so that's why we change the velocity of the field. We convert it to the velocity relative to the ground. Okay. And our task is, of course, to find the v as a function of time. Okay, so let's do it. Now let's do it by considering the momentum change of the system. Now suppose initially at a certain time t, the rocket is flying with a velocity v. That is what happens at this instant. And in a short time later, I call this short duration delta t, the rocket has ejected some field. The field ejected is q delta t, because q is the mass ejected per unit time. So q delta t is the mass ejected in a small time interval delta t. And so correspondingly, the mass of the rocket will also be reduced because the field is being ejected out. So the mass of the rocket will become m minus q delta t, where m is the mass at the beginning, and at end of the time interval, because the field is ejected out, the mass of the rocket is reduced by Q delta T. Okay. Now the ejection of the field will cause the rocket to accelerate. So that means there will be a change in the velocity, which we call delta V. So V plus delta V will then be the final velocity of the rocket. Okay. Now it's important to notice that the field here is ejected at a speed of V minus U relative to the ground, because we now will apply the conservation of momentum. So it's important to calculate the velocity correctly, and that's relative to the ground. Now we further assume that the system is not affected by any external force, including gravity. Now this is not generally true, but I hope this simple example will not include gravity for simplicity. Okay. Now so we can apply the conservation of momentum. This is the total initial momentum, and these are the final total momentum, right? So we apply the conservation of momentum at time t and time t plus delta t. At time t, the momentum is simply mv. While at time t plus delta t, the momentum will consist of the momentum of the rocket itself and the momentum of the field. The momentum of the rocket itself is m minus q delta t, the new mass, multiplied by the new velocity v plus delta v. So the first term here is the new momentum of the rocket. The momentum taken away by the field is the mass of the field multiplied by the velocity of the field being ejected. Okay, and that velocity is relative to the ground. Okay. Now, if you expand this bracket, totally, you will find 4 terms in the first term, and 2 terms in the second term, right? If you expand it all. Now, I've omitted the term with 2 delta. If you encounter this term, delta t multiplied by delta v, I will ignore it. Now, I ignore it at this moment. I will let you why. Okay. So I just expand all these brackets. The first term is mv. The second term is m delta v. The third term is minus qv delta t. The fourth term is minus q delta t delta v. This term I've ignored it. Okay, I've ignored the term with 2 deltas. Okay, and also for the second term, I now have qv delta t as the first term, and minus qu delta t as the second term. Okay, now you see a lot of terms can be cancelled. The qv delta t, these 2 terms cancel. The mv on both sides also cancel. And I now left with only 2 terms. M delta v and minus q u delta t. Okay, now I rearrange this equation. I divide the whole equation with delta t and take the limit where delta t tends to 0. And of course, delta v over delta t now become dv dt. And on the right-hand side, I now have qu over m. Now this equation can be integrated over with respect to t. But be careful. Q is a constant. We assume to be constant. The field is ejected at a constant rate. The U is also a constant by assumption, but the M changes with time. The mass of the rocket actually changes with time because fields are continuously being ejected. So the mass of the rocket at time t is equal to the initial mass of the rocket minus the mass of the field being ejected, that have been ejected. Okay, so it's equal to m naught minus qt. Qt is the total mass of the field ejected in a time t. Okay, so we put this m back to the equation, and we find this differential equation. This differential equation can be integrated over. I move the dt to the right-hand side, and on the left-hand side, I'll only have a dv. And on the right-hand side, I have all the things that only involve the t. Okay, so I can integrate both sides. On the left-hand side, I integrate from initial speed of v0 to the final speed v. So it becomes v minus v0, and v minus v0 is a change in the velocity. Okay. Now the right-hand side is also not difficult to integrate. If I make a change of variable to m0 minus qt, okay, that involves a factor of minus 1 over q coming out. Okay, I just make a change in variable from t to m0 minus qt. And by doing so, I have to add an extra factor of minus 1 over q, okay, to cancel the q that goes with the t. Okay, and that means that this guy can be easily integrated over, and the result is a logarithm. The initial time is 0, the final time is a general time t. So what is the result? The q here cancel, the u here, and when I evaluate at the time t at time 0, because there's a minus sign, I invert the 2. So the upper limit will become at the denominator of the logarithm m0 minus qt, while the lower limit will now be at the numerator, which is m0. With the minus sign, I invert the upper and the lower limit. Okay. And now this become what? This become the logarithm of the initial mass divided by the final mass of the rocket. Okay. And after multiplying the logarithm by the velocity of ejection, I will get the change in velocity of the rocket. Now you notice that the logarithm is a slowly varying function. Imagine the logarithm of the base 10, for example. If you have 10, then logarithm 10 with the base 10 is 1, right? If you increase by 110 times, you have 100. But logarithm of 100 is only 2. If you increase it by 100 times, that goes to 1,000. But logarithm of 1,000 is only 3, right? So you increase from 10 to 100 to 1,000, but still the logarithm only increased by 1 or 2, right? So the logarithm is a very slowly increasing function, especially when it goes to a large value of the argument. So that means although you can make m0 over m very large, you can make the rocket to contain a lot of fuel, such that the final mass will be much smaller than the initial mass. After you eject all the fuel, the rocket will contain less and less mass. So you can make this factor very large. But since it involves a logarithm, that will not give you a very large value. It may give you a value of only 2 or 3, a number that's order 1. So the delta V will not be very large. So delta V will be at most several times the fuel ejection speed u, okay, which is not much. So that's why it is very difficult to accelerate a rocket. Okay, you need a large amount of fuel to just accelerate a rocket by a small by high speed. Okay, you need to expel a lot of gas to produce a substantial change in speed. That is the problem of launching a rocket. Okay. Now this is how a modern rocket works. It consists of several stages. After the fuel in each stage has been used out, that engine will be disposed in space. Okay, so eventually, when it deposes a different stage of the rocket at different time, eventually it will left only the launch above system that goes into the orbit. Okay, so that means all the mass of the rockets they almost consist of solely the fuel that need to eject, that need to accelerate the top part. Okay, so that is to make m0 over m very large. Okay, so that's why most of the mass of the rocket actually consists of fuel and the engine, and they will be disposed after use. Okay, and this tiny small part that is entered orbit will consist of a very small mass. Okay, so that means a large amount of fuel is needed to accelerate a small spacecraft into space. Okay, so that's the idea. Okay. Now we have finished the chapter on momentum. So let's go to the chapter on let's talk a little bit about the chapter on rotation. I've just uploaded the first part of the natural laws of rotation into the blackboard, so you can download it now, or you can do it later after the. The rotation is a long chapter. Okay, so I divided natural laws into two parts, and I only will introduce the first part in these few lectures for you. Now let's deal with the rotational kinematics. Now, when we measure rotation, the important thing is that we are no longer using the linear position of the object. When we discuss about one-dimensional motion, we measure the position of the object along a line, right? We assume it to move back and forth along that line. But now for rotation, we measure the position of the object not by its linear motion, but by the angle that the object moves. So when the object is, for example, at this position, we draw a line to connect the object with the origin. And we choose a reference direction to measure the angle of the object. And normally for two-dimensional motion, we choose the x-axis as a reference line for measuring the angle. So the angle that makes with the x-axis would be called theta. And the theta is the position of the object and that angle is measured in radian. We always measure the angles in radian because we use differentiation and integration, which are calculus. And calculus rely on the angle used in radian. Okay. Now remember that the radian is dimensionless. Because the radian is by definition, can you remember the definition of radian? The radian is the arc length divided by the radius, right? You imagine an angle subtend a part of the circle. This is the center of the circle. This is the angle theta. This is radius r, and this is s, the arc length subtended on the circle. You have the radian defined as s over r. And that means the radian is dimensionless because s and r both carry a dimension of length. So s over r is dimensionless. So radian is dimensionless. Now we are concerned with the angular change in position. So delta theta is the position of the object at time t plus delta t minus the position of the object at time t. So that is again an angle. We are not measuring the change in the actual length now. We are measuring the change in angle, which is called the angular displacement. Okay. If we divide the angular displacement of the object by the time taken for the object to do that displacement change, that will become the average angular velocity. Okay, so the angular velocity is by definition the change in angle divided by a time taken. But that's average over a period of time, a finite period of time. So I called it the average angular velocity. So by this formula, I have 3t plus delta t minus 3 theta t divided by delta t. Now this diagram gives you a heuristic understanding. This is the position at time t, and this is the position at time t plus delta t. So the difference between the two angles will be this delta theta. Okay, so I divide the delta theta by delta t, I get the angular velocity. But that is the average quantity only. Okay. because the angular velocity might itself be changing with time. And if I take the limit where the delta t tends to 0, the ratio of delta theta over delta t will then be equal to d theta dt. And I call this the instantaneous angular velocity. The instantaneous angular velocity means the angular velocity at a certain instant. The angular velocity may be changing, but the instantaneous velocity always refers to the angular velocity at a certain instant of time. Okay. Now let's look at the angular velocity. Let's look at its dimension. It is the angle moved by the object per unit time, right? Because the angle divided by time. So the dimension of the object is radian per second. Okay, the radian is the angle. Second is a unit for time. So the dimension of this object is radian per second. But since radian is not a, does not carry any real dimension, I can simply write as per second. Now for me, I prefer to write radian per second. There's no harm to write like this way. It makes me remember that it is the angle per unit time. Okay, although radian itself does not carry any dimension, so you can skip this in your unit. But for me, I prefer to write this like this because it helped me to remember that I'm calculating the angle per unit time. Okay. Now there's also another quantity that is commonly used, especially for rotation, and that's a linear frequency. If you consider an object rotating about on the XY plane, rotating about the coordinate origin, then the linear frequency of the rotation means the number of cycles per unit time. That means how many cycles does the object complete in a certain time. That is the linear frequency. So the unit for linear frequency is cycle per second or simply per second. How many cycles per second? But the cycle itself also does not carry dimension, so you can simply write as per second. Now there's a special name, special unit for the linear frequency, and that unit is Hertz. Hertz is a famous scientist who discovered the radio wave. He did an experiment on radio wave and find that the spark that generates somewhere in the room can affect the instrument on the other side of the room. So he proved that the radio wave actually travel between the two sets of instruments. Now Hertz refers to the number of cycles per second. It always refers to the linear frequency. Now, so never use Hertz for angular frequency omega. The Hertz is a specific unit used for the linear frequency. It will not be used for a angular motion, angular frequency, okay, or angular velocity, okay. Now, we describe the motion with an angular velocity, but you can always refer omega as the angular speed if the direction is not concerned. Okay, so you can always say about the angular speed instead of the angular velocity if you are not concerned with the direction. Now, because one cycle is 2 pi radians, okay, so the linear frequency and the angular frequency that are related in a simple way. Omega is simply 2 pi f. When you say that the object revolves around the origin three times a second, that is a linear frequency. So you multiply that 3 with 2 pi, because one circle is 2 pi radian, right? You get 2 pi multiplied by 3 radian per second, and that is the angular frequency or the angular velocity. Okay, so the angular frequency and the linear frequency are just related by a factor of 2 pi, which is the angle in a circle. Okay. Now, we can define the angular acceleration similarly to what we did for its linear counterpart. When we divide the change in angular frequency by time, the change in angular frequency is the angular velocity at time t plus delta t minus the angular velocity at time t, okay, divided by time. And that is called the average angular acceleration, okay? When the time delta t become infinitesimal small, when we take the limit delta tends to 0, it becomes the angular acceleration. And the angular acceleration is just the omega dt. And if you like, you can express the omega further in terms of d theta dt. And so the alpha will become the second derivative of the angle theta with respect to time. And this is called the angular acceleration. This expression refers to the angular acceleration, okay? And the angular acceleration has a unit of the radian per second square, a radian per second square. So we are using this angular quantity to measure the rotation of the object, okay? So for linear case, we have the displacement. Now we have the angular displacement theta. For the linear case, we have the velocity. Now it goes to the angular velocity, which is the angle turned per second. For the linear case, we have the acceleration. For the angular situation, we have the angular acceleration, which is the angle per time square. Okay, it's a change in angular velocity per unit time. Now, in the next lecture, we are going to talk about the similarity between the linear motion and the angular motion. And also, for the special situation where alpha, where the angular acceleration is a constant, we can just essentially copy the linear motion formula to the angular case, because the mathematical structure between the linear quantity and the angular quantity, they are just identical. They are almost identical each other. So when you have angular acceleration which is constant, I can use the equation of uniform accelerated motion, but with all the linear quantity changed to angular counterpart. Okay, now so in the next lecture, I will talk about this. And after a brief review of circular motion, I will talk in details on how to formulate a rotation of a rigid body, a body as a whole, and a whole body rotating about certain angular velocity about the axis. Okay, now so let's stop here. Let's stop the recording now.